This is section 8.1, day 1, and today we're going to start a chapter all about sequences and series. Lots of you are familiar with these from last year, talking about arithmetic, geometric, and how to write those formulas or find those sums. So the very first day we kind of just start off talking about some notation. And all of sequences and series has like this, let me focus that for you, has a usually a term, and then it has a subscript after that. So kind of contrary to where you've usually seen them, which is an exponent, now we're talking about doing a subscript. So this, an AN, usually means the term you're on. You are on. So then if I had a plus 1, this would mean the next term. Kind of like what we were doing, or will be doing in inductive proofs. And then n minus 1 would actually be the previous term. So that's just a little bit of the notation that you'll see in this chapter, in this unit. So the first one says write the first 4 terms of the sequence. And the formula or the sequence is denoted by a sub n. So all we're going to do is find the first 4 terms. That means I'm going to plug in a 1, I'm going to plug in a 2, and a 3, and a 4. So that subscript is actually telling me what I'm going to be doing each time. So first we'll plug in a 1, a 2, 3, and a 4, and that's how we're going to find the first 4 terms. So 2 times 1 plus 5, 2 times 2 plus 5, 2 times 3 plus 5, you probably already see the pattern. Oops, sorry, times 4 plus 5 is 13. Next up, we're going to do the exact same thing, only this is just an exponential, so we'll have to be a little bit more careful when we're doing our math. So 3 to the 1 minus 1, that's 0, and 3 to the 0 is 1. Second term, we're plugging in a 2, so now I've got 2 minus 1, which, whoops, I meant to put an equal sign, which equals 3 to the first, which is just 3. The third term is going to be 3 to the 3 minus 1, which is 3 squared, which is 9. And the fourth term will be 4 minus 1, which, darn it, instead of 4, wrote a 4, which is 3 to the third, which is 27. So this pattern had us multiplying by 3 each time. And it doesn't really matter what I start the sequence off, like what letter it is. It could be any letter here. You're just kind of looking at the notation and how it translates on this side. So every time you put something in for the subscript, like a B of 1, saying you're finding the first term, just says you're going to put a 1 there and you're going to put a 1 there. One more to go. First term, we're going to plug in a 1, so I've got 3 plus negative 1 to the first. Any negative number to an odd power is going to remain negative. So we'll actually have 3 plus a negative 1, which is 2. Second term, now we're going to raise that to an even power, and when you do that, you end up getting a positive. Back to an odd, so negative 1 to the third power is going to remain negative. And 1 to any power is still a 1. We're just kind of messing around with the negative back and forth. And then this will be a 2. And I'm sure you can see the pattern that as soon as I flip this back to an even power, it's going to turn it positive. So that sequence is just kind of flipping back and forth, 2, 4, 2, 4. Next up says write an expression. Okay, so now instead of you getting the formula and you coming up with the terms, I'm giving you the terms and asking you to write the formula. The first couple days that we are in this chapter, we don't really care about whether things are arithmetic or geometric. Those are only 2 different types of sequences. You can have arithmetic, which we'll talk more about in the upcoming sections. You can have geometric, same there, we'll talk about it later. And then you can have neithers. All of these can have equations written for them. All of these can be found out for a sum. So you can do the same things with all 3 of them. Students just prefer these 2 because they come with their own set of equations. For neither, you're kind of on your own and you got to come up with your own equations. So that's what we're going to try to do here. So this very first one, first I tell kids, try and see if there's a pattern. So for us, looks like we're going up by 2 every time. Then I also tell kids right above the terms, write down what term it is. This is the first term, the second term, the third term, the fourth term. Sometimes you're trying to see what the pattern is between the number and then what term it is, seeing if you can distinguish a pattern that's happening. I'm just noticing how close 7 is to almost double of 4, like double of 4 is 8, and then I kind of just check that. Double of 3 is 6, double of 2 is 4, so I'm just off 1 every single time. So it looks like, remember, these are the things you're going to plug in. We plugged in a 1, 2, 3, 4. So whatever formula you come up with, I have to be able to plug that in. So it looks like I'm coming up with, I'm doubling my number. Every time I plugged something in, I was doubling it. And then I was just off by 1. So I was, if I took a 1 and plugged, if I took a 1, plugged it in, times it by 2, and then subtracted 1. Each of these, when I double it, was just off by 1. And so that is my formula. I'm just double checking it. If I plug a 1 in, I just check that one. If I plug a 2 in, 2 times 2 is 4, minus 1 is 3. That's my second term. Plug a 3 in, 3 times 2 is 6, minus 1 is 5. So looks like I came up with a pretty good formula that's going to work for that sequence. What you are going to hate about the next 2 days is that there is no straightforward, cut to the chase, figure it out way to do it. And sometimes you're going to have to struggle with it a little bit, try a couple things, see what doesn't work, see how close you get. It's guess and check for a lot of it, which frustrates students because you guys kind of are used to, or you want a formula that you get to just plug into. So these ones are going to take a little bit more brain work. First, I'm going to look at the pattern. So 2 to 5 is adding 3, 5 to 10 is adding 5, 10 to 7. Okay, so I'm adding odd numbers. That's not, it's not an easy pattern to like duplicate. Like over here doing the same thing every time, that kind of resulted in this nice little 2 right there. But that's a little different. And they're going up fast. Like I'm going to add 3 and then I'm going to add 5 and it's just getting bigger. Add 7, that's more than this. Different than adding the same amount every time. So I'm adding bigger numbers faster. I'm going to go ahead and put 1, 2, 3, 4 at the top because I want to kind of relate what term it is to what actually comes out of the equation. So seeing if I could see a pattern there. Kind of doing my times 2 thing in my head. Timesing by 2, actually that works. 2 times 2 is 5, or sorry, 2 times 2 is 4, not 5, so that won't work. 3 times 2 is 6, like that's even more off of 10. 4 times 2 is 8. I'm even farther behind of 17, so that's not going to work. I actually need something that goes up a lot faster than multiplication. So multiplication is not bad, which is what we were doing back here, but multiplication, if you remember from elementary school, is just repeated addition. So that's why multiplication works when you have the same thing being added. We don't. We have bigger things being added all the time, so we need an operation that actually goes faster than multiplication, and that is exponents. So exponents go faster than multiplication, and we are climbing faster than just addition, straight addition, like a 2, 2, 2 or a 3, 3, 3. So now I'm going to think about exponents. So what if I squared this? So 1 squared is 1, so I'm off. 2 squared is 4, but I'm off by 1, so that's the same. 3 squared is 9, I'm off by 1. 4 squared is 16, I'm off by 1. So I think I found it. So whatever I decide to plug in, I'm going to square it, and this time I'm actually going to add 1 because we were always short one number as we were going along. So I'm just going to check it to make sure. 4 squared is 16, plus 1 is 17, that works. 3 squared is 9, plus 1, that's 10, that works. So it looks like I came up with a possible solution. That works. Keep in mind that what you come up with is not always the only formula out there. There is another formula that you could have come up with, well, this one specifically because it's arithmetic, and it would have been the same thing. If I were to simplify it, it would be the same thing as this. So just because maybe you've got something different than what I've got on an answer key or what your friend has, doesn't make it wrong. If yours produces this sequence, then you're right on. Next up, let's go to fractions. Students seem to struggle with these because I think in general we don't like fractions. And lots of students try to figure out, how do I make 7/6 as a whole thing turn into 9/7 as a whole thing? And oftentimes it's very impossible, or completely not, you're not able to do it. Sorry, I'm trying to spit my words out here. So we're going to look for a pattern on the top, looks like +2, and I'm going to look for a pattern on the bottom, looks like +1. I actually want to treat the top and the bottom like they are separate things. So don't see them as one fraction, see them as, what is the top doing? I'll even cover that up. And then what is the bottom doing? And we're just going to work with each of those separately. We'll write a formula for each one. So on top, I'm doing a ×2 thing. So it's very much like this one. Sorry, not a ×2, a +2, which is very much like this one. This one, we kind of quote-unquote ended at 7. We know it continues. This one kind of picks up at 7. So I'm going to try to use the exact same formula and see what happens. 2 to the n 2 times n minus 1. But this is my first term still, so I'll just put a 1 there, 2 there, 3 there. And I know darn well if I plug a 1 in, 1 times 2 is 2 minus 1, that's 7. That's not 7, so I have to come up with something just a little bit different to get me up to 7. If I times by 2, that's okay. I just think I need this to be much bigger. Excuse me. So 2 times 1 is 1. To get up to 7, we'd actually have to add 6, so let's see if that works. We'll do 2 times 2, which is 4, plus 6 is 10, and that's too big. 2 times 3 is 6. 6 plus 6 is 12. That's too big, so I'm off by just a little bit. Oh, I didn't check my first one. 2 times 1 is actually 2, plus 6 is 7. I was off by 1. That's why it didn't work. Let's try 5. So 2 times 1 is 2, plus 5 is 7. 2 times 2 is 4, plus 5 is 9. 2 times 3 is 6, plus 5. That's 11. So the formula I figured out is 2n plus 5 for the top. On the bottom, we're just going up by 1s. So kind of using the pattern that we found out, the 1, 1, the what you're going up by, the 2, 2, kind of becomes what you multiply by. And then we got to adjust a little bit in order to get to 6. Remember, this is your first term, second term, third term. So you're going to plug in a 1. 1 times 1 is 1, but to get to 6, we're going to need a 5. 2 times 1 is 2, plus 5 is 7, so that works out. 3 times 1 is 3, plus 5 is 8, that works out. So it looks like that is my equation. And again, fractional sequences are so much easier to figure out if you deal with the numerator separately from the denominator. What we have worked on so far is something called an explicit formula, and now we're going to talk about something called a recursive. So explicit is kind of a, if I wanted to find the 10th term, I could just plug in a 10, I could figure it out. Recursive doesn't allow you to do that. Recursive means you have to reuse, that's the re part. So you can't get to the 10th term without knowing the 9th or the 8th or the 7th, like you have to know them all in order to get to number 10. And recursive formulas always have 2 parts. So they have to tell you the first term, we got to figure out where to start, and then after that they tell you the pattern. So first term, we were used to that notation, is a 3. After that, the formula says to find any term, you just have to take the previous term, we did that notation up above, and add 5. So try not to get bogged down by that notation, it just means previous term, and it's telling us add 5. So if I want to find the second, this was the first, this is the second, I'm supposed to take the previous term, 3, and add 5, 8. In order to find the third term, I'm supposed to take the previous term, 8, and add 5. To find the fourth term, I would take the previous term and add 5, 18, and so on and so on. Next, recursive 1 actually starts with a that should have a 1. Starts with a -5, so your first term is a -5. And the equation after that just says in order to find a term, you take the previous term, and we're going to multiply by -3. So if I want to find the second term, I'll take the previous term, -5, and times by -3. To find the third term, I'll take the previous term, multiply by -3, -45. And so on. So recursive just says you have to reuse. There's no way for me to go out and find the fifth term until I know the fourth, and I can't find the fourth until I know the third. So you can only build your way up. You can't like jump out and find the term that you're kind of looking for. Last thing in this section is talking about factorial notation. And lots of students remember this whole exclamation point. Doesn't mean they're really excited numbers, but it stands for factorial. And factorial just means that number times every whole number below it, all the way down until 1. So every whole number below that number, and you're multiplying all of that. So then the 2 factorial underneath will be 2 times 1 only, and then 8 would be 7, 6, 5, 4, 3, 2, 1. And while I'm showing you this kind of way written out kind of laboriously, you could totally plug this in your calculator, just make sure you have parentheses. I'm showing you the process so that when I do something that has no numbers in it, we can recognize what the process is for factorial. So once I get these two numbers stacked, I'm just going to start crossing stuff out. I've got stuff in the top, stuff in the bottom that match, so I'm just going to cancel. Then I've got a 2 into a 5, so it leaves me with 5. So I've got 45 as my total sum. Next up, we're going to do one with no numbers. So now what if I had just an n? So n factorial, same as if it was 10, would have started with 10 and then decreased. So we need to start with n and then decrease, and then decrease, and then decrease. So we have to keep decreasing by 1 every single time. So this would be like 10. This would be 10 minus 1, which is 9. This would be 10 minus 2, which is 8. So just showing you how they kind of compare. So you start with whatever the factorial was, and you just go down by 1 until you get to the end. So if you started with 100, you got a long ways to go. But once you get to 3 and 2 and 1, then you know you're done. As soon as you hit that 1, that's the end of your factorial. On the bottom, we're actually going to start with n plus 1, which is weird, but let's just pretend that this was 10. Then our n plus 1 would actually just be 11. It would just be 1 more. So we're still going to start with that. That's your beginning factorial. And then you're going to go down 1. So if you were at n plus 1, you would just be at n. And then you would be at n minus 1. And then 1 less than that. And then all the way until you get to 3 and 2 and 1. You really only need to do your factorials until you start to repeat, because everything after that will be repeated, just like here. 10, 9, and as soon as I started with the 8s, everything after that was going to repeat itself all the way down. So I know that all of this is going to cancel with all of that. As soon as I started to repeat information, all of it's going to match up all the way down. So on the top, I'm left with a 1. Everything canceled. On the bottom, I'm left with just n plus 1. And that is factorial. So this is just our first day, our first kind of steps into sequences and series. This part will probably frustrate you the most, is being able to come up with your own equation for the sequence. But keep guessing and checking and see if you can figure them out.